to DV1-178. This has been an evil idea that's been in the back of my head for a couple of years, and I finally managed to sucker Professor Brown into being my co-conspirator for it. Some of you I've had the privilege of having class with before. Some of you I've had the displeasure of having class with me before. I don't know, some of you maybe have had Professor Brown before. So who's had Brown before?
Nobody.
Nobody. Oh, well.
They have no idea what they're in for.
Yeah. Well, they're 50%. They know 50% what they're in for. Okay. So Dr. Brown and I are going to co-teach this course. And basically, because we've never offered this course before, we're kind of in the experimental stage, if you will. So you guys are all guinea pigs for the semester. But we're hoping to have some fun. Basically, the idea for the course was to take an intro electronics course that might be something offered in physics and an intro CS course that, I've taught that sort of stuff lots of times, and basically go smush and kind of do the two together in a way that I think either discipline on their own misses something. So we're going to be live streaming basically all of the lecture parts of class, but not the lab parts. And we'll kind of talk about what the distinction is between those as we get going. This, as you guys realized with the way it's scheduled, there's no separate lab. It's just going to be integrated in with the class. And so basically every day we'll do some part that's sort of lecture-y and then another part that's more labby. And for obvious reasons, we won't stream the labby part because we'll all be walking around doing stuff. There's no point putting that up on Twitch and YouTube. So the live streams for the lecture part will go up on my Twitch stream, and then I copy them over to the math department YouTube page basically once a week for posterity's sake, which is real handy for two things. One, it's January, you're going to get sick. Somebody's already sick, right? It's going to happen. So if you have to miss class for a good reason, not, oh, it's 8 a.m. and I overslept, right, Mr. Stolte? Yeah. Then, no big deal. You can always grab notes from a buddy, but we'll also have the stream. And then second, and this is the other reason that I've kept doing this, at least in my own teaching, is I've got the play count analytics to show that even if I have everybody in the room, I still get like 30-something play counts on a given video, which means you guys are going back and reusing the things after the fact. And those of you who have had me before for classes can confirm or deny that scandalous rumor. Did you go back and use the videos? Yeah. So anyway, so that's the other reason that I'm doing it. So I'm Dr. McKinney. I'm a mathematician by training, but have been teaching computer science almost exclusively for 4 or 5 years now. All of my computing knowledge is pretty much self-taught, just because I'm a giant nerd face. And this is Professor Brown.
Hi, so I've been kicking around this place for something like 20 years, so some of you may have heard of me. Basically, I'm a nuclear physicist. I teach physics. My background is primarily in development of devices related to high-speed data acquisition and interfacing. So we slow it down a little bit for a sensors course because sensors tend to respond relatively slowly. Here's a question for you. How many of you own a smartphone? Excellent. What do you think about how that thing knows, say, well, I'll tell you what, who's got an iPhone? Excellent. Why don't you ask Siri what the barometric pressure is? Barometric pressure, the air pressure.
Hey Siri, what's the barometric pressure?
Should give you, she gave you a web link or she give you a number? She gave you a web link. All right. So usually she'll give you a number. You might ask what your altitude is. The two are related, and so she uses it to calculate altitude. Your phone has a sensor suite that includes things like a gyroscope. It knows how it's oriented. It knows it knows on 3 axes what the acceleration is. It knows the current air pressure. It knows the direction on that gyroscope relative to magnetic north. And all of that is available as a sensor suite that's integrated onto the chip. And then that connects to the CPU on the little computer. So by the way, how much, so let's just say this. How much of a computer is this?
I would say it's a computer.
Yeah.
What was the question?
Well, kind of what, describe it. Well, let's put it this way. Compare this, the storage on this, to the storage of, say, the Internal Revenue Service in 1990. Yeah, significantly more. Right.
And in terms of, say, the computing power, right, my watch has more computing power than the entire Apollo space program, both in the air and on the ground.
Yep.
And certainly oodles of more storage than that. So, you know, the capabilities of computing devices have been growing exponentially for basically since they were created in the 1940s, or at least say electronic computers.
Yep.
And a good metaphor for this, and those of you who've had me for another class, I've used this before, would be if the automotive industry had moved from its beginning at the same kind of rate that the computing and electronics industry had, your car would get 1 million miles to the gallon by now, and the cars would get so much better so quickly that if, let's say you wanted to go on a date and you wanted to take somebody to dinner and a show in downtown Indy, okay, seems like a, you know, good evening, right? It would be cheaper for you to just throw away the car when you got there and buy a new one after you got out of the dinner and the show than it would be to pay to park the car. Right, because the cars, after that 5 hours period, would be so much better than the 5 hours before. I mean, it's maybe a bit of an exaggeration, but not entirely outrageously a bit of an exaggeration. So what we can do with these things has just skyrocketed, literally. And you know, we're going to be working with some relatively simple computers and some that are a bit more modern in their capabilities, but then also kind of looking back at, well, how do you even build these things in the first place? What are the fundamental, like a computer, right? We treat computers nowadays as sort of like a magic box, right? You don't really think about what's actually in the iPhone or how it works. Now, there are nerds at Apple that do that. But, you know, what is it about a computer that's going to be similar and dissimilar from us putting things together on a circuit board? I think you guys will find that things are a little messier than what you think to some extent, but also, you know, we can very easily, with 6 or 8 little parts, put together the fundamental building blocks of a computer, and then you just need to imagine billions of those. And then you get your iPhone or your computer.
Yeah.
So
We'll cover a bunch of that stuff. So you should have 2 books. Has everyone looked at the academos for the books that are available?
and they are
Conveniently.
located here. So the green book, Raspberry Pi for Dummies. You guys are all dummies. Not really. And then Electronics for Beginners. But I've got great news, because what did I discover yesterday, Anton?
They're both available through ebook form from the library.
Unlimited copies, which means, yeah, so you don't have to actually spend any money. Although I think you guys have probably found that Dead Tree is pretty handy to have. So, yeah, and we tried to find books that were relatively inexpensive. Don't order it. I probably shouldn't say this on the stream. Don't order it from Academos.
You can't say that.
Oh, I can't say that? Okay. Well, the Academos police are going to come down and arrest me, so it's nice knowing you guys. I'm going to go off to the textbook gulag. So, yeah, anyway, they're both relatively inexpensive. I think they're like $20 each, roughly. Yeah, and they're pretty, you know, good. The For Dummies series is maybe a little silly, but particularly for a lot of you that have never really dived into how a computer works under the hood, or ever used, how many of you guys have consciously ever used Linux? Well, okay, those of you who have had me in a few classes before. All right, how many of you have unconsciously used Linux? Does anybody have an Android device? Android is basically running on a Linux platform. And the computers we're going to be using, in addition to obviously computers you guys have, we're going to issue you guys Raspberry Pi laptops, and those are running a Linux version. We'll talk about that in a little bit, and sort of get into the details as to how it works. Those of you who use Mac computers will actually find it more familiar. Those of you who use Windows, it'll look a little different, but there are some structural similarities between Linux and Mac OS because they're both kind of derivative way back in the day from a sort of a common ancestor. And so a lot of stuff will seem familiar, but there's a graphical interface, and so that makes it pretty easy to do pretty much whatever you want. Although we're going to teach you guys some of how to use console commands. So back in the day when Brown and I started learning computing, well, Brown, you had to trudge to a terminal in a library somewhere.
True.
Or carry a stack of punch cards to a library somewhere.
No, punch cards are dead.
Okay.
We did use those in my house, though. Dad would pick them up from the chemistry department and leave notes like, shovel the walks on the stove on the back of a punch card.
So when I started learning computing, there were, graphical interfaces that they hadn't been invented yet. Or not really, they were being invented, I guess, at the time.
You don't predate Xerox PARC.
No, but I mean, my Commodore, my first computer didn't have a graphical interface.
That's true.
So, yeah, so we'll talk about, Linux and operating system stuff. The course is really designed from a computing perspective. Those of you who want to go on to CS111 in the future, great. Some of you I know have already taken CS111, and heck, we've got some senior CS majors in the room, right? So you guys get to program in Python and assembly when I deem fit. The rest of you will get to program in the block languages. So if you've never programmed before in your life, don't freak out. If you've done a lot of programming in your life, well, you're fine. Brown and I realized that this is kind of going to be a one-room schoolhouse sort of thing. And we'll have fun with it, hopefully. So, yeah. Now, how many of you guys have never done computer programming in your life? Okay, that's fine. And then where are our CS majors? Right, okay. So actually, it shook out that
Okay, so we got a lot of CS.
we ended up with more than I was anticipating. But this counting for a lab class, I think, sort of did that, right? Yeah. How many of you guys are here because this counts as a lab class? Yeah. Is anybody not here because it counts as a lab class? Yeah, that's what I figured. Okay. So anyway, well, since we're going to require you guys to have 4 lab classes now, then you might as well get this one in, right?
Who spread that?
Me. Well, the 3 started with James Skalky, but I just jumped on the bandwagon to have a little bit more fun. So it's fun trolling you guys on Yik Yak.
Except everyone knows who you are.
Well, yes, and that's sort of the in joke, right? So anyway, okay, so that's sort of the big picture about the course. Anything you want to add? And then we'll kind of start to get into some of the details.
Well, we did have some attendance things, right?
Oh yeah,
like-
the syllabus stuff,
so
yeah.
we still have a little syllabus-based stuff to do. Basically, we're going to be a bit of a hard ass on attendance, primarily because the lab's integrated and we're going to be doing something every day, with the exception maybe of today. So if you're not going to be able to be here, you get to throw yourself on the mercy of the triumvirate, I guess.
Yeah, the 2 consoles.
The time for the 2 consoles. Excellent. And let us know, and we'll work something out. Try not to do that too often. If you don't do that, we've got some draconian penalties, so you can read about them in the syllabus.
Yeah. So show up to class early, right? Those of you who have had the joy of me at 8 a.m. in the past right? To be early is to be on time. How many of you are seniors and this is your last lab science credit? We own you, okay? We literally own you. And I don't want to stop you from graduating.
We only own their graduation.
Oh, okay, right. Yeah. We own your graduation, right? So
You
show
can
up on
still work at
time
McDonald's.
and be ready and be, not hungover or whatever. I mean, although you guys usually wait till Thursday before you go up to the Cactus, right? Yeah, okay. So we're all good since the class meets on Thursday.
Is the Cactus still even open?
It reopened.
It reopened.
Yeah.
Okay.
Anyway, so yeah, it is critical because of that you get to class every day because of the lab part, right? That is hard to replicate outside of this time, and there will be draconian penalties. So show up, and if you're sick or you've got a dean's excuse, although there's not usually too many of those in the morning classes, right? Things happen.
Right.
Brown and I are somewhat reasonable, but only somewhat.
Right. Don't
So-
show up if you're hacking and sick. Let us know, because there will be some crud that goes around this semester.
Right, it's inevitable.
Right.
So anyway, yeah, show up. In terms of like how we're gonna do stuff, so we'll have a midterm and a final. The midterm we'll do kind of right before spring break. The final is scheduled. I've got that up on the top of the syllabus. We're going to be doing a bunch of labs. Essentially one per day, and they might kind of span multiple days. Exercises. This will be kind of your traditional, like written homework kind of stuff. We're going to do a collaborative project, and we'll talk a little bit more about that. But Brown and I had one idea for a project, and then something serendipitous dropped into our lap. Is anybody an art major or minor in the group? Okay, film and digital media. No? Okay. So Wabash, the art department, the fine arts broadly, periodically bring in visiting artists that stay for the course of a semester and maybe teach a class or participate in a class, and they also set up some art installations and do workshops for students and so on. Well, it just so happens that this semester the visiting artist is a guy who does a bunch of digitally inspired art that uses sensors and computers and screens and lights and all kinds of things like that. So the collaborative project, basically, you guys are going to make art, but you're going to do it with the cool little toys that we've got. So we'll talk more about that later, and we're kind of excited about it because it's sort of a serendipitous thing, and hopefully we can do some hashtag liberal arts college stuff.
Does he have an installation set up at the college as well, or is it just the one downtown?
He will if it's not already set up.
Okay.
Yeah, what Dr. Brown is mentioning. So how many of you guys have been to the Carnegie Museum of Montgomery County? No? Okay, so those of you who have been in a class with me, some of you have. The Valero that's now the Marathon, the super sketchy gas station? It's sort of right across the street from that. Huh?
Super sketchy?
Well, it's mild.
You've got to recalibrate your super.
Well, okay, it's mild.
You don't get your fifth in a little turnstile. You put your cash on one side and they turn your...
Okay, but at the checkout counter, I don't know if they still have this. This was like 5 or 6 years ago. I went, was grabbing a drink, and I'm paying, and in the little cabinet, they have like a box with urine in it. And I'm thinking, that's weird.
You asked him why I was there?
No, I did not, but my students informed me that it was not as creepy of a reason as I thought it was. It was beating drug test urine, not people with weird kinks kind of thing. So, yeah.
So wait a second. They sell clean urine for drug tests?
Well, they did at least.
Interesting.
Yeah.
I see no issue with that. That's they're doing a service right there.
A service? Yeah.
To
Okay.
whom?
It was just a little weird, okay, when I'm sitting here buying a drink and then what's, a foot in front of my face is that. So, anyway. Huh?
You didn't want that?
No. Tends not to be very thirst quenching, I'm told, right? So anyway, the Carnegie, so it used to be the public library here in town. For those of you who are from the area, who all is from Montgomery County? Yeah, 1, 2, okay. Used to be the public library up until maybe, what, 20-something years ago?
Yep.
And then they built a new library across the street, you know, much bigger building that's kind of right there by Arnie's. And the Carnegie is still owned by the county and the public library, but now it's sort of a museum instead of a library. Lots of local history, kind of some natural science stuff, mostly targeted at the K through 12, you know, kids basically, and then also stuff that, you know, their parents can enjoy if they take them. Owen Lowry, the artist, has an installation there with some stuff, and then he'll also have some things over in the art galleries, or the art gallery space in the Fine Arts Center. And so, you know, we'll get you guys more info about that. You know, should be interesting to talk with him about it. And
We should post the first expedition assignment and make them go
over there.
Go over this week and write a paragraph about it.
Yeah, maybe we'll wait until it's not 20 below zero, but
These are Wabash men.
yeah. So, yeah, but anyway, the stuff at the Carnegie's already installed, so it should be interesting to go see.
Yeah.
All right, any other syllabus things? There's a bunch of boilerplate things on at the bottom here, college policy. So a couple of important ones would be, of course, accommodations. You know, those of you for whom this applies, you know the deal. Talk with Heather, you talk with us. Counseling center is available, contact there. Health center, right, if you do get sick, it's gonna happen to somebody. Info there. Quantitative skills center, supplemental instruction, doesn't really apply to this course, but it may to your others, so take advantage of it if it does. Writing center, again, not super relevant to this course, but not completely irrelevant. And then we'll talk about generative AI, the whole ChatGPT thing, et cetera, because it's useful in some cases and really a disaster in others. And then OSE is Dr. Koppelman, and then you guys don't have to worry about the 4th hour because this is a lab, so we're all in compliance, and that's good. And read the syllabus. We'll issue you these other 2 things and any other handouts and parts that are necessary. And then there's the links to the 2 books on the library's website, and of course you can also order them if you so choose. Anything else on the syllabus?
I think we're good.
Okay. Any questions on the syllabus stuff? No? Okay. So, let's close this. Do you want to do Class 01 first?
Yeah, I can go first.
Not 07?
Yeah.
Okay. All right. So, I'm not a huge PowerPoint guy, but sometimes it's the right tool for the job. Yeah, so basically each class we're going to work through the material that's going to be in a couple of the chapters of both books. So, you know, electronics or dummies as appropriate. And today we'll talk about a little bit of both of them. We'll get our hands dirty with some of these parts later in sort of the lab part of today. But we want to go through some intro stuff to kind of get going. Okay? All right. Do you want to drive or do you want me to drive?
I can drive.
Okay.
All right. Drop this into, we're running from here?
Yeah, just use the keys.
All right, fine. Are we in presentation mode? No, we're not. Here.
No, because then I can't see the stream controls. Right.
All right.
So
we'll just use.
I'll get a clicker for you.
No, it's fine. All right. All right, so let's talk a little bit about simple circuits. So this is what's called a schematic diagram of a circuit. And it describes the connectivity of the circuit. It doesn't tell you how to physically lay it out. And what it says is you have a 3-volt battery. That could be like 2 D cells in series would make 3 volts. So they're about 1.5 volts each. The D cell and A cell, C cell, they're all 1.5 volt batteries. Then you go from the positive end of that through a resistor, then through an LED, and then back to the negative end. So one thing you'll notice is it's a loop, right? That's what a circuit means. Circuit literally means a loop. And everything with electronics is in the form of loops or nested loops. And the real simple thing is any electrical current which flows out of the battery needs to go somewhere, right? And it's only got one choice in this circuit. And this circuit never branches. So it goes through the resistor, where it generates a little bit of heat and uses up some potential. The same current then moves down through the LED, where it generates some light and some heat, and then back into the battery. So the energy is flowing out of the battery, it's being dissipated as heat and light. And we're going to spend some time talking about how to go from that kind of a diagram into laying something on what's called a breadboard, and we have some breadboards. But if we go back to the first slide, there's one next to the book. So I think our task for today is a little bit to sort of figure out how one of those breadboards is connected, and we'll pass those around. And there we have probably give you a multimeter and a breadboard and a couple of wires in groups of 2 to figure this out.
Yeah. So eventually, probably next week, we'll issue you guys each one of these buckets that has a bunch of parts in it. I only have enough buckets for pairs right now. We're putting together the extras. So we'll just work in kind of pairs today until we've got all the buckets ready. And then also on the computers, when they're ready for checkout, we'll give you instructions for what to do, where to get them.
Yeah, we'll expect that to happen probably later today. They'll be ready, and you can start checking them out on Wednesday in the morning.
Yeah. So anyway, so the breadboard is that little thing in the on the cover of the book, and essentially we will wire things to it. This one happens to be wired up to a circuit board called an Arduino, and that's actually what we're going to use today also for 2 reasons. One, today it's just going to be something that provides us power. That's it, real simple. But you know, we could use power from batteries even. Doesn't have to be anything fancy. But that circuit has a couple of different parts. It's got an LED on it, and one of the things we'll start to talk about is how do you go from a diagram like this to actually putting it on the breadboard like that without doing it incorrectly. Because you'll notice in the diagram, there are certain important pieces of information that we need to make sure that we don't mess up. So for example, the battery, how are batteries labeled? Yeah, positive and negative. And you guys have all put batteries into a remote control for a TV or some other device like that, right? What happens if you put them in backwards? Doesn't work, okay? So the direction of some of these components is important, but not necessarily all of them. So the resistor, it actually doesn't matter which direction you put it in. But some of them do. So for example, the LED, what does LED stand for? Anybody happen to know? Yeah. Right, it's a diode. And what is a diode? Anybody happen to know this? Yeah, Anton.
Restricts the current to one direction.
Right, it's essentially a one-way valve, if you will. Like if you imagine current being like water flowing through a pipe, can you imagine like a little flap or something that if the current's trying to go backwards, it can't, but it can go one forwards, right? So a diode sort of does that. And the LEDs just happen to also produce light in the process, which is useful for, you know, because we can make blinky things and stuff. But if we plug the LED in backwards, what's going to happen? Nothing.
Yeah, it can't conduct current, so it's just essentially you put an infinite resistor there.
Yeah, so learning about which parts have directional components and which ones don't right? That's part of the purpose of the schematic, right? So you notice, for example, either the battery or the LED symbol, there's information there that tells us which direction it's got to go. Whereas with the resistor, it's just a squiggly line. It doesn't matter. One other thing, I guess, on the subject of the circuit here, so which way does the current flow? In the diagram, in this case, yeah, it would flow clockwise. Okay, I could redraw the diagram so it flowed counterclockwise, just flip it, but in this drawing, it's counterclockwise. Okay, now how do you know it's counterclockwise in this diagram?
Because we know that the LEDs only allow the current to flow one way.
Okay, good. Let's say there wasn't even an LED here. Which way does current flow? It goes from positive around to negative. Okay, so current flows from positive to negative. Why is it, huh?
Let's not get into carriers yet.
Okay, yeah. And we can blame Benjamin Franklin for that convention.
Right.
As we'll discover later.
It just throws some minus signs into an equation. It's not
Yeah,
a big deal.
he had two choices and he chose poorly. But anyway, that's the convention. Current flows from positive to negative. Negative sometimes we talk about as being ground. That is especially the case with, like for example, if you want to plug something into the wall, right? We got the wall outlet here. There's 3 prongs that go into it. What are the 3 prongs? Yeah.
They're not positive, negative, and ground.
It's hot, neutral, and ground. But yeah, the ground, and not all plugs have a ground on them. Now, the wall plugs are a little weird, though, because they're a different kind of current than what we're dealing with here, but we'll talk about that
Yeah, we'll get
later.
to that in the 3 slides.
Huh?
We'll get to that in 3 slides.
Yeah, so, okay. So there's our simple
All right.
circuit.
So here's what's called a multimeter, and you're going to have to learn how to use one of these. Basically, it's a device that can measure resistance. So it has 2 probes, and if you connect the probes, one of them to the common and one to this volt ohms, then you take your sample and you stick it between the 2 probes, and it measures the resistance of that sample. And that sample could be a resistor, it could be a piece of wire, although it's going to measure very low for a wire, and it might be below the reading limit of the thing. It'll also, if you turn the dial to the volts, but if you look at that, you see 2 kinds of volts. One that's got a solid line with a dashed line under it, and one that's got a wavy line after it. What do you think those 2 represent? Yeah.
Alternating and direct current.
Yeah, so the DC, the direct current, is the solid line, and then the wiggle is supposed to represent a sine wave, and it's the alternating current. Because alternating current is the easiest to make mechanically. You just take a coil and you spin a magnet around that coil, and it produces an alternating current in the coil. And the wall current does that 60 times a second, going positive, negative, positive, negative, positive, negative, moving the current back and forth. So in fact, the average electron in a wire, yep, we're here, in a wire that's carrying the current, even if it's like the current out of a power plant, one of those big high voltage lines that come out carrying millions of watts, essentially, those guys, the individual electrons never move more than a millimeter or so. They just don't.
Yeah. So essentially what happens is the electrons are moving back and forth and back and forth, and that movement back and forth, energy is moving, and that allows us to power things. So for example, all the lights in the room or the lights in your dorm room are connected basically directly to the AC current of the wall, and you can't see this, but they're really actually flickering 60 times a second.
Well, you can see it. If you're in a room with fluorescent lights that are old school 60 times a second, if you wiggle your hand like this, you'll see individual copies of your fingers. If the light's on all the time, you'll just see a blur back and forth.
Now, nowadays with LED lights that are much more common, partly because they're much more energy efficient, that's not quite true because there's a thing in the light that's going to convert from AC to DC, and then the DC will give you a continuous light stream. Same thing is true about electronics. So yeah, go ahead. Sorry.
Is that why when you have like a higher frame rate camera, you see sort of a wave effect on some screens?
Yeah.
Yeah.
Yeah. And it was especially prominent back when people were using like VHS tapes and old school like cathode ray tube monitors, right? So maybe you've been to your grandparents' house or something that has a giant tube TV. You know, back in the day, that's all we had. And yeah, so cameras will pick up that flicker, and people that do high-end videography have equipment that synchronizes to wash that out so you don't actually see it on camera because it's really distracting. You sometimes also will see this on like, I've seen like videos on YouTube where they're reviewing cars and things where the headlights will sort of look flickery. Same issue. Yeah.
Yeah, then you pick up a new problem with modern cameras, right? So a film camera exposes the film with just the light that hit the film, right? Electronic camera, light hits the film, but you read out this line, then this line, then this line, then this line. And if the image has changed in the time that you're reading the lines, you can get what's called a rolling shutter effect. Look up rolling shutter in propeller aircraft sometime.
Yeah.
It's a very interesting thing because that prop is moving.
Yeah. I mean, and you can see the same thing with like a ceiling fan or like a floor fan, right? Where you turn it up to high and it actually looks like it's moving backwards, right? It's sort of the same kind of visual effect. Okay, so yeah, AC versus DC, right? I think it's a great band.
And no one
Yeah.
laughed at my joke, but you know, all right, they just don't read the.
Yeah, you guys all know AC/DC, right? Right? Okay, great. So yeah, AC is what comes out of the wall. DC is what most electronics are going to use. And why is it you have to carry around those big annoying bricks with your laptops and stuff? To convert it, right?
Yep.
Your laptops, electronics use DC, but the wall is AC. So you got to have some sort of gadget to convert from one to the other, and those are the little bricks that you have to carry around. It used to be the case, actually, that wall power was DC, way back in the day.
There was a short war
Yeah.
about that.
But AC won out because it's way more efficient.
It can be transmitted over greater distances more easily.
Yeah.
Because
So
of the transformer.
anyway, so yeah. But for our cases, for the most part, we'll be using DC, or excuse me, DC. And then the AC will basically just be the wall power.
Right. And you shouldn't be playing with the wall power if you don't know what you're doing, because unlike a 9-volt battery, that 120 volts AC can do you some damage.
Yeah,
Not
it's pretty
great.
painful. How many of you have been stupid enough that when you were a kid, you stuck your finger in an electrical socket, right? Not so comfortable, was it? No, very, very uncomfortable. Yeah, I made that mistake once myself, once and only once.
What?
Whereas a 9-volt battery, right? If you short that out across your body, is it going to hurt? I mean, what's the way that you test whether or not you've got a good 9-volt?
Lick it.
Yeah, just touch it to your tongue real quick. Does that hurt? It tastes funny. It's not exactly comfortable, but you're also not just leaving it there, right? You just do it real quickly. If you stuck your tongue in the wall outlet there, well, let's just say we'd have French fried Wally, right?
Yeah.
Not a good move.
Right. Cooked tongue.
Yeah. So, yeah, cart you off to Sparks and serve you for lunch.
All right, let's go down 3 slides.
Okay. So 1, 2, 3.
All right. So when you're using a meter, like in this circuit diagram, I've stuck in an ammeter, which is a current meter, and a voltmeter. The thing that's different about using the two different ways is the voltage or the potential is what is across an object, so you measure from the low side of the object to the high side of the object. You stick your probes on one end and the other end. But current flows through something, and the only way to measure a current easily is to interrupt it, cause it to flow through something. Like if you've got a flow meter on a water line, can it be outside of the line? No, it's got to be in the line. There's got to be some little mechanical thing that turns as the water goes by. That's not really the way an ammeter works, but it, in fact, does have to have that same property, that the current needs to flow through it for it to measure it. So you need to break a wire, stick your ammeter in, make the measurement. You don't have to go with a voltage
Yeah, so
probe
that's
to
this
do it.
part right here. To take the measurement of the current, you basically interrupt the current so that all the current goes through your measurement device and therefore allows you to measurement. Whereas with the, if we want to measure the voltage,
Yep. So if I close that switch in this one, what's going to happen?
so the switch is labeled there S1
Yep.
at the top. So if we close it, what does that do to the circuit? Yeah, the circuit actually is complete, right?
Okay.
Is it complete right now? No. If we close the switch, it is, and then what?
We get a voltage reading.
Yeah, current's going to flow, and we
So-
should get some sort of voltage.
So, right, so the current will flow out of the battery, and then it has to make a choice when it gets to R1 and R2, which one it's going to go through, right? And more of the current will flow through the one with lower resistance and less with the one with higher resistance. And then when it gets down to R3, it doesn't have a choice, right? The currents need to recombine, and all of it flows through R3, and then it flows back into the battery. So basically, always remember, current is a continuous thing. It always, whatever comes into a node goes out of a node. You don't get to build up. Current doesn't get stuck somewhere. So is that voltmeter going to read more or less than the voltage of the battery? We got one vote for less, one
We've got
vote
one
for
vote for the same.
Less. So what about the ammeter? Is it going to read the entire current flowing through the battery or not? Yeah, so it'll read all the current, right? Because the current had no other choice than to flow through the ammeter. There was not another path for it. And the reason we only get part of the voltage out is that some of the voltage has to be across that R1, R2 pair. And that leaves some left over to go across the R3 pair. And we'll talk about how to figure out how much later. All right, so let's go down to the next slide. So the first chapter on the book talks a lot about units and safety, and so we'll talk a little about units here. Our typical units for electric circuits are going to be volts, amps, and watts. Volt is a measure of the amount of energy required to move a certain amount of charge from one end to the other. Typical D-cell batteries like 1.5 volts. The wall is 120 volts RMS AC.
For the circuits that we'll be working with, the voltages will basically be 9 volts and under,
Yeah.
right? So we'll do some stuff with 9-volt batteries. Those are obviously 9 volts. The Arduinos and things that we'll plug into will provide either 3.3 or 5 volts, depending. So pretty low voltages. This also, therefore, will mean relatively low power and low risk of you electrocuting yourself.
Yeah. Well,
Essentially no risk of you electrocuting yourself, but
if you can electrocute yourself with a 9-volt battery, you've worked at it.
or licked it.
Yeah, you worked hard
Yeah.
to kill yourself with a 9-volt battery. Anyway, yeah, a 9-volt battery will deliver 9 volts until you actually ask it to also deliver some current, and then it'll drop off.
Right.
So the real thing to watch out for is current limits. Most of these little LEDs are limited to significantly under 30 milliamps. If you go over that, you're going to let all the smoke out that the engineers spent a lot of time putting in it, and it will no longer function. and it will smell unpleasant.
Yeah, so don't short out the parts. And this is why we have to use the resistors to basically keep the parts from putting too much current through a given component. And we'll talk about how to correctly calculate those so that you know in advance it's going to be fine.
And the book pissed me off in my reading the other day because it talked about resistors as dissipating current. Why did that really tick me off?
Doesn't dissipate imply like disappearing, like being neutralized completely?
Yeah, and so in fact, the current never goes away, right? The current goes through one thing and into the next thing. It doesn't ever dissipate. What does dissipate is heat. You generate some power. All right. And keeping that power for most resistors under 1/8 of a watt is a good thing. If you go over 1/8 of a watt on most of these resistors, again, you let the smoke out that the engineer spent time putting in there, and it smells funny.
Also, the components start to get hot, and you could, the odds of you burning yourself with these things are much more, well, burning.
If you put more than 1/4 watt through one of these resistors and then touch it,
It's not going to be comfortable.
you'll know it
Yeah. So, and that's
for
bad.
several days.
Yes, that's bad. Okay. Yeah. So, you want to go back up to the safety stuff, just real quick?
Yeah,
Oops.
there we go.
Okay.
Never use the wall power. If it smokes, turn it off. You've done something wrong. All right? Calculate first. LEDs don't handle more than 30 mils. Calculate first. Some components have voltage limits. Read the, let's see. RTFM, always a good slogan. What does RTFM stand for? Exactly.
Oh, you're going to get me a content strike on Twitch. So it's read the manual.
Read the fine manual.
Yes, exactly.
Yes.
Yeah, and calculate. I mean, this is the same sort of thing. Like, how many of you guys have worked with, power tools, saws, that sort of thing, cutting wood? What's the adage when you're cutting wood? Measure twice, cut once. Right? It's the same thing here. Measure, calculate, make sure that you're good, double check everything, then plug it all in, and you'll avoid a lot of headaches. Okay.
And some of the things we're going to work with are like logic chips and things. Those are semiconducting components, and they're a little sensitive to what's called electrostatic discharge, or ESD. If you're going to handle a chip, it's best to ground yourself to something grounded first. A metal case of a laptop connected to its power supply will work just fine. So you just put your hand on that, that'll be fine, and then handle the chip.
Yeah, you don't want to be like rubbing a balloon up against your head and then touching the chip.
Yeah, or scrubbing around on the floor with your rubber shoes, and then grab hold of it. How many of you have grabbed hold of a doorknob after scrubbing your feet on the floor this time of year?
And what happens?
Yeah. How far can you throw a spark from your fingertip to the doorknob, basically? Think gonna be like that far? You know what the breakdown voltage for that much air is? Roughly? Roughly speaking, that's about 2 kilovolts. So it takes about 2,000 volts of potential to generate that spark. These things have operating voltages of like 5 volts. They don't like having 2,000 volts put across them. They operate on picocoulombs of charge, and probably transferred in that shock. A million times that or more? Yeah.
Yeah, so the chips part, and we'll get to those later in the course, like with your computers, right, they are relatively sensitive. Now, computers are shielded and there's metal and lots of stuff, but it is possible to screw them up. So you just have to be careful and don't, if you're careful, then this should be pretty straightforward.
Yep.
Okay, so yeah.
All right, so we go down. Oh, units. Everyone loves units and prefixes. All right.
And everybody especially loves the metric system, right? Oh, yeah. Yeah, because hashtag not Merca.
What?
Yeah,
Oh, it's not American.
Yeah.
Wait a second. But
Merca.
Merca.
Yeah, Merca. You know. So, yes. So of course the metric system is the symbol or the system of science and most of the rest of the world in terms of measuring things. There's only a few things in this country that we tend to measure with metric. Power, electricity stuff is actually one of them, believe it or not.
Yep.
But there's others like, you go out and buy a 2-liter of soda, not a 2-gallon of soda. Or pop for those of you who are from those parts of the country.
Or Coke if you're from Texas.
Yes.
Everything's a Coke. You want a
Yes.
Coke? I've got lemonade and Sprite.
Yeah. Well, Texas is special. So with any metric unit, often we need to put prefixes on it so that we don't have to write lots and lots of zeros or decimal point zeros, right? And you guys probably learned all of this back in what I would hope elementary school, right? The metric prefixes. Yeah. So some of them you maybe haven't had to use for a while, and some of them are maybe a bit more specialized to, talking about electronics, particularly like micro and nano, right? And then there's some of them that we tend not to just use, like, for example, hecto and deci and deca.
Not that common.
Not that common to be used. People just tend to go straight up to kilo or down to centi or milli. Mega, giga. I mean, how many of you guys saw Oppenheimer this summer or since, right? So there's that scene when Oppenheimer is saying, well, we'll have to measure it in tons, and somebody says, well, it's going to be thousands of those. So he's like, okay, fine, kilotons of TNT, and then, then they get, of course, bigger bombs. For our purposes, at least with the electronics, we'll basically be completely under the unit line. I can't think of any reason that we would need to use any of the larger ones.
Like kilo ohms.
Oh, yeah, okay.
Mega ohms.
Yeah, so resistances are going to be in, the unit is an ohm, and the smallest ones that we'll use are like 220, 330 ohms, but we'll also use 1K, 10K, 4.7K, things in that kind of range.
In general, 10 to the 3 multiples, like kilo, mega, giga, tera, those are the ones that are most commonly used. The 2s and stuff, as Professor McKinney said, are the rare ones.
Yeah, so we're all good with the metric system? Yeah.
All right.
Not rocket science, but,
Well, it is rocket science.
well, okay.
All right, so hey, guess what? There's going to be some math in the course. It's everyone's favorite subject, right? Look at those faces, how excited they are to be doing some math. No one's excited at 8 in the morning. It's kind of sad, actually.
Yeah, it is.
Just Anton's excited.
If we can bet on it. Yeah, but see, then we'll have to start doing parlays and like 3-leg parlays or whatever
good
Jacob
Lord.
was trying to explain to me.
You know how much money is wasted going into fan zone and sports?
Well, I don't know. Is it more or less than however much you guys spend on like Clash of Clans? Way more? Okay. Yeah. All right. So yeah, there's going to be some math, unfortunately.
So basically, we're going to be doing relatively low precision computations. So electronics components are fairly crappy normally. The engineering value and the actual value can be off by about 5%. So in that case, you should never need more than 2 digits. And the safe thing to do is calculate with 3 and round to 2, and you should be fine. Sometimes you're going to use scientific notation. which is just breaking off how many powers of 10 there are. In this case, we've got 2 times 10 to the 2.2 10 to the 3, which we write as 2200, or 2.2 kiloohms in this case.
The Greek letter omega is the symbol for ohm, and you'll learn these as we go, the different letters that we attach to different quantities. So ohm is the measure of what? Resistance. Yeah, resistance. Okay. Okay, good. So
right.
in the circuit diagrams, right, you're going to see lots of parts, and sort of here's a partial diagram of what the component might look like in the real world and how it looks in the schematic. So let's go through these. Right, we've already talked about the battery, right, and batteries have a directionality to them. A wire is just a line, okay? Resistors are the squiggly bits. A light bulb has this symbol. We also saw the symbol for an LED. That symbol is like if it's an old school light bulb that we tend not to use much anymore. Junctions are like that, and often when I make the diagrams, I'll put a little dot if they actually connect, and I won't put a dot if the wires are just crossing over each other. But in more complicated diagrams, that may be something you have to think about. Capacitor, what's a capacitor?
There's something that holds charge, and if you get like a motor going, like direct power, it like holds the charge.
Yeah, exactly. So it's literally 2 separated pieces of conductor that can get charged up, one positive, one negative. And then you can use that separated charge to drive a current pulse as you discharge it. And yeah, the biggest thing you'd want to use it for would be typically starting an electric motor from stationary. You also use them in your AC to DC power supply. The simplest design for that is like this. A very complex design. AC power source. Diode. Capacitor. And this is then nominally DC. And basically what happens is that single diode is there letting each forward going pulse through, and it charges up the capacitor. And while the AC is in the wrong direction, you're running your device off the capacitor, and then it recharges the capacitor on the next pulse. All right, so let's go down to the next one.
Yeah, and then switch, that's obvious. Okay.
All right, get out a piece of paper. Here is a drawing of a circuit. I want you to draw it like an engineer would, like a schematic diagram, like the ones I drew. Or I use DigiKey's schematic thing to draw it. Yeah.
Are we putting this in or can I just do it on
Huh?
Are we turning this in or can I just do it on
Yeah, you are not turning this in.
Right.
This is, and you can even talk to your neighbor. This is not an assessed exercise.
Oops.
I'm going to give you about 4 minutes, so get moving.
And then we'll draw it here together.
It's on the next one. It's on the
Oh,
next
okay.
slide.
Okay.
I took a picture with my phone. It was very exciting.
Oh.
Yep.
We've got somebody on the Twitch stream, which I'm not sure if it's
It should be
our
it should-
missing
it-
person.
It should be
or-
Mr. Ill. Mr. Ill, who sent an email early in the morning. Finally got out of the way. What you probably ended up with was something which more represented the way it's drawn here, right? As in the spatial relationship stayed the same. Your 75 ohm resistor's probably still over here. Your 100 ohm resistor, you might have tilted it straight up, I don't know. But you probably left it like that. But remember, the circuit diagram only talks about the topological way things are connected. It doesn't talk about geometry, how things are laid out on the circuit at all. It doesn't, and this does not say how to put things on the onto the breadboard, the circuit board, whatever. It doesn't say that. It just says how they're connected. So the easiest thing to do is start from the positive terminal. Okay, go from the positive terminal is the first thing we do. Go through the 100 ohm resistor, right? Positive terminal, 100 ohm resistor. And from here we have two choices. We can go down through the 75. Okay, so we're down through the 75. And if we go through the 75, we only have one choice. Go through the 125, right? Okay, so 75, 125. There's that choice. All right. And then let's look at the other side. The other side, if we made the other choice coming out of the 100, we could have gone to the capacitor. And then from the end of the capacitor, we go directly back to the other side of the battery. There. And from the bottom of the 125, we go back to the battery. And so this has the same connectivity as that, but is a cleaner schematic representation. So how many people got something
Basically that
basically
looks
looks like that?
What variations are there that are correct, but just look different? Yeah.
Yeah.
I just had the capacitor and the resistors on the opposite lines.
Yeah, you probably put the resistor pair over here.
Or
No,
in
I
the,
put it like where the capacitor is.
Oh, so you put it here and you just switch these two.
Yes.
Okay. Yeah.
yeah,
yeah.
you could rotate the figure.
Yeah. Yeah, so you could have done that. I'm a little surprised that a bunch of people didn't actually just leave it on the same side it was and then put the resistors over here. So that's the more natural thing. So people, what they end up doing is initially sort of confuse the idea of the circuit diagram with the physical layout, that's what matters, when what matters is just the connectivity. And so then it's easier to put, for me, I always tend to put my power on one side and then the objects on the next, if it's fairly simple.
Yeah. So there's lots of ways that you can draw these and that are all technically correct. There is sort of an aesthetic to it, right? You don't want to just like, you can make the wires be all squirrely for just to irritate people, but why?
Then
right?
they roll up your, then your boss rolls up your blueprint and then beats you with it.
Right. So you know, you want to be somewhat smart about how you do this, but there are, of course, because the diagram is representing how things are connected to each other, which is what we call topology, there's lots and lots of ways to draw it that all represent the same piece of the same information. And you just want to do that representation in as much of an elegant way as possible. And then, of course, here, notice that all of the resistors are labeled in some way, or all of the components are labeled with what their values are, right? Because if you were actually putting this thing together, is there a difference between a 75 ohm and a 125 ohm resistor? Yeah, right? And does it matter if you get the wrong one in the wrong place? Yeah. So label the things. Often, if we go back way to one of the very early slides, often these things are also labeled R1, R2, R3, so on, or LED 1 and so on, right? So they may have another label there that you can then use to refer to in like a manual or something. but some of the software automatically puts these things in if you're making it. And we'll talk about some of the software you can use, but just doing it by hand, that's pretty good.
All right, so we'll move on to the next one. All right, so now I want you to calculate. So there's one very simple relationship between the voltage across a resistor and the current through it. The current flowing through a resistance requires a voltage drop of I times R, where I is the current and R is the resistance. So we have a very simple circuit here. We have a 12-volt battery, a 300 ohm resistor. I place a current meter here and a voltmeter here. So I want you to figure out what the ammeter reads and what the voltmeter should read. So calculate like an engineer. There you go. No one has any guts? 0.04. Okay, 0.04. For what?
The ammeter.
Okay. Anybody got the voltmeter? Nobody?
Is it just 12 volts?
12 volts! Yes. Excellent.
It's a trick
You
question.
can go to the
Yeah.
next slide. It's not a
All right.
trick. It's a
Well-
perfectly valid question.
Yeah.
All right. So you calculate the 12 over 300, you get 0.04. And any reasonable human doesn't like 0.04, but they do like 40, so it's 40 milliamps.
Yeah. Now, if we actually read the voltmeter, like the actual device, would it read exactly 12?
No.
Probably not. It's probably going to be like plus or minus a little bit. But,
Yeah, it depends on what the precision of the battery is and
Yeah.
how good your ammeter is.
but for just a mathematical exercise, it'd read essentially 12 volts.
The two digits will probably be good.
How does the reading on the ammeter change if it's before the resistor in the circuit?
If I moved it to this position here,
No, I'm saying after, so if we're looking at the charge going like clockwise
yeah,
around the circuit, if you moved it to,
this position,
yes,
same. Why?
is why.
Well, okay,
All
think
right,
about it.
who has an answer for why? Because is a shitty answer.
Yeah. It is just is, but
Well, so what? So okay. So think about it. What's an electric current? Something's moving in the wire, right? What's moving? Okay, electrons. Now the problem is that was alluded to earlier is the electrons are moving in the opposite direction of the electric current because they're negative. That was the problem that was. So in order to get a positive current, an electron would need to leave the bottom of the battery and go up through the resistor and into the positive side. That gets confusing, so we're just going to imagine that there's some mythical positive carrier here, all right? So our little charge-carrying canoe comes out of the, carrying 1 unit of positive charge, comes out of here, and it goes down this wire. And it has a choice to go to the voltmeter, but that's very, very high impedance, so it probably is not going to make that choice. It's going to make the choice to go down here, and it's going to come down here, and then where's it going to go? Back to the battery. So if I send 1,000 out here, they go through the resistor, they come here, how many come back in here? There you go.
They don't get stuck anywhere along the way.
They don't get stuck anywhere. That's the answer to your question, right? The current's continuous in that sense. Whatever comes in goes out. So that's what's called a node rule. If you have so for instance here, the current technically has a choice. It can so it comes in here, it can go out there or there. 99% of it's going to go this way, and less than 1% is going to go to sort of make the voltage measurement.
But notice what happens on the other end.
It comes back in.
They both come back together, right?
Yeah.
So flowing water is a crude analogy for,
It's not bad.
but it's not terrible either, right? If you had a hose and your amp meter would be like the little spinny thing that tells you how much liquid is flowing, and it's flowing, let's say, from the spigot on the side of your house, and let's say you're just dumping it into a sewer, right? How much water ends up in the sewer? Exactly the same amount that comes out of the spigot, right? It doesn't get stuck anywhere unless you do something silly like try and kink the tube or something along those lines, right?
Right. Well, yes.
Yeah.
So, yeah, don't take the water analogy too far because when I was about 10, I was visiting my grandma. It was the middle of the energy crisis, and she was trying. There were knots in all of her electrical cords. I said, "Grandma, why you got these knots in your electrical cords?" She goes, "So I won't use as much power." Thinking like a hose. If you tied it in a knot, less current would flow.
Yeah,
By the way,
work
it does
that
not
way.
work that way. It absolutely does not work that way. Yeah.
Following the same analogy of like a fluid, what is voltage in this case?
Well, so it'd be pressure, or right. Right. More pressure would cause at one end of a pipe would cause more fluid to flow through it, right? So, for instance, if I had a big old water tank high up, at the bottom there's so many feet of pressure, right? And that's what provides the pressure to push the water out the bottom. If I put that same pipe closer to the surface of that tank, high up, not as much water would come out of it, right? Because there would be less pressure. In fact, if I put the output pipe right at the surface of the water, how much water comes out? None, right? If I put it just an inch below, not much. Put it 30 feet below, a whole bunch, right? And that's why do we have water towers anyway? Yeah, it's literally so that you don't need to run the pumps all the time in order to make the city's water work. You just pump it up into the tower, and then the pressure's there for falling water to provide all the pressure. As long as the elevation change is good, water towers are great. If what you don't want to do is have a water tower at the top of the mountain and try to then use that to run the taps in the village down below. You do not want 3,000 feet of pressure on your pipe in your house, because you will very soon not have a pipe.
Yeah, of course, big towers also usually have a small, like big apartment buildings like in New York or something, tend to have tanks up at the top for precisely this reason. You know, they're not as big as, say, the municipal water tower that's over by Kroger, but they don't need to be that big for just one building.
You know another fun fact about high rises?
No?
Yeah, you got to take the sewer lines that go from the toilets and stage them into little pools on the way down every couple of floors, so you don't drop a turd the whole way and pull everyone else's water out of their toilet bowls as it goes by.
Okay, no, that makes sense. Yeah, so, all right.
Engineering at its best.
Okay, so this is good for the start of the electronic stuff. Do you want to go ahead and move to the other?
Yep, your turn.
Okay, my turn.
When do you want to give them a little break?
Let's just do that now. Let's just take a quick break and take a quick potty break. So let's take 5 and we'll get back to it.
All right.
So what I'm going to show you guys, at least just initially, is a little bit about the computer that we've got. And once it gets going here, accept all the cookies and read online. So what we're going to be using are computers called Raspberry Pis. And here's sort of a picture of what one looks like. So the Raspberry Pi is a very inexpensive computer that was designed for basically educational purposes. It's basically about yay big, you know, so like a small, like credit card size. Thank you. The HDMI is not working on the laptop. I think there's like a weird refresh rate issue that I've got to figure out. But I'll figure it out. Yeah, it worked fine on my office, but my monitor there maybe I think is a little more forgiving of refresh rates than so. Anyway, okay, so yeah, so they're these small little computers. They are not particularly powerful in terms of computational power. The chips that are in them are like 10 years ago smartphone kind of power, right? So they're quad-core ARM chips that would have been in kind of low-end cell phones maybe, 10 years ago or so. But that's enough to run a relatively robust computer. Are you going to be playing high-end games on it? No. Could you maybe play Minecraft? Probably, right? And certainly they're great for programming and stuff. But the real reason that they're going to be useful to us is not just because they're a computer, but because of all these little pins that are over here. So the Pi as a machine, like I said, is just a perfectly good computer. You could just use it as a desktop computer with no trouble. But these pins here allow you to, within programs that are running on this computer, turn the pins on and off, and also read information from the pins. So what that allows us to do would be to connect sensors to the device, and we could connect other electronic components to the device and control them using logic that we program on the machine, rather than just wiring everything up on a breadboard. Okay? Which means we can do things that are more interesting than just wiring things up on breadboards, because we now have computer control of the thing. It also has a couple of other ports, so like you could connect cameras and displays and stuff to it, and do some kind of neat stuff like that. But basically, that's all it is. So what's on the back here is an Ethernet port for networking, although it also has wireless. USB ports, HDMI ports, so they're the micro HDMI, so they look a little funny. USB-C for power, and then these GPIO pins. Now, for convenience purposes, I was able to get IT to buy us a bunch of shells, and I'll show you what those look like. Called the CrowPi L for laptop. And essentially, it's a laptop shell that you pop one of these Raspberry Pis into. And it's got a couple of little auxiliary circuit boards to drive the keyboard and screen and things like that. But what it allows us to do, right, so you just basically pop the thing in the underside, is on the side of the unit, and you can't really see it quite in this picture, on the right side of the unit is a little breakout where those GPIO pins are wired, and that will allow us to wire things into it. But the other benefit of it being in sort of laptop form is we don't have to have it plugged into the wall. The laptop thing has a little battery in it, so we can run off battery power, and it's much more portable, right? You don't have to lug around a monitor and a keyboard and a mouse and a power supply and all of that crap and plug them all in and then tear them all apart. We can just walk around with these things as if they're laptops. Now, they're not exactly laptops, and we'll talk about So like, for example, turning them off, you have to be a little careful how you do that. And they don't go to sleep the same way that a normal laptop would because they're not really laptops. They're, really think of it as it's a desktop with a trench coat put on, okay? Yeah? Oh, come on, I should get more humor, more laughter than that, right? Okay, so these things are running an operating system called Linux, and you've probably never used Linux before, most of you. So let's just go to getting started with Linux and kind of look at a few things there. Now, the screens are going to look a little bit different than in some of these pictures versus what I've got installed on here, but it's not substantively different. For the most part, it's going to look like a computer that you've used before, right? This sort of looks like a Windows computer, except where's the Start menu or the Start button? Where is it on Windows nowadays? It's at the bottom, either the left or the middle, depending on if you're running Windows 10 or 11, right? Or if you just your preferences. Here it's at the top. Okay, whatever. You can reconfigure that. But the little Raspberry logo, or for us it's just going to be a grid of squares, is basically your Start menu. And everything that you could possibly want to use, okay, is there. So if you click that, right, or you click our little thing, you're going to see a bunch of software organized into categories, okay? And a lot of the software is going to be stuff that you're familiar with. So for example, Microsoft Word, you guys use that, right? Well, you have to pay for it, right? You know what I like doing is not having to pay for things. So there's a free version that's sort of Office compatible called LibreOffice that's developed by a group, sort of open source group, and they basically have the full productivity suite that you could want, right? So you've got Base for databases, calculators like an Excel thing, Draw for drawing pictures, Impress for doing like PowerPoint, Math. You can do like actually lay out and typeset math and have it look good. And then Writer is basically like your Word thing, right? Basically works exactly like Word does. Looks slightly different, and it's free. By the way, not only is it free on these machines, but you can put it on your own computers too. Although I guess, how many of you guys use Google Docs instead nowadays, right? So yeah, you got choices nowadays. Now, for our purposes, right, where do we really want to be doing stuff? With programming, okay? And there's a couple of different languages that you can program in, one of which is called Scratch. Let me come back to this. And let me see, so programming. So Scratch is a visual language. Let me show you kind of what it looks like. Looks like that. How many of you guys have programmed in Scratch or another block language like this before? All right, so those of you who did Scratch, how many of you did it in like middle school, elementary school, high school, somewhere in there? Okay, has anybody done it in a context other than that? No? Okay. So those of you who've never really done much programming before, programming in these graphical interfaces is very handy for novices because it's very difficult to make certain kinds of errors that frustrate novice programmers. But think of it as programming with training wheels. And eventually, we're going to remove the training wheels. But to start, it's pretty handy. Now, the CS guys in the room who have all programmed in Python and other things, everything you can do in Scratch, you can do in Python and then some, right? So you guys will get to do this in Python from the get-go. Everybody else, can I help you? Yeah. Yeah. You're a little late, bro. So, actually, I've always wanted to do that is, you know, go into a class like on the day of the final and pretend I'm a student in the class and I haven't been there all semester and Just be like, yeah, so what was this class again? What's up? But yeah. I mean, how many of you guys have the dream where you're like showing up to a final for a class that you've never been to, or
I get that with like plays and musicals and stuff.
Okay, yeah.
Performing a musical that I have never seen the script of before.
yeah, and half the time you're not wearing clothing or any those silly dreams. It's just the dream of showing up to a class you didn't know you were in for the final, or
Oh, we could teach it. It's different. They want to take differential equations. I think that'd be great for these guys.
oh right, yeah. So okay, so Scratch, you can do a lot of stuff with Scratch that you can make little simple video animations. You can make like little games, right? And those of you who did it in like middle school, high school, what did you guys make with Scratch? What were the kinds of things you did?
We made like basic games.
Okay, simple games. What else? That sort of thing. Yeah, Mark.
It would be the same thing if you're like on a CRM and you're making like workflow automation for a data.
Yeah, actually, okay. Yeah, so that actually is a good point, that visual scripting or visual programming is used in a lot of industries, even the real world stuff, okay? And now let's think about it like a customer relations management software, right? Like something like Salesforce, for example, right? Why is it maybe a good thing that, say, your Salesforce software, you can program in sort of this graphical, in a graphical manner?
You don't have to like hire people to code for you.
Yeah, exactly. So your dude that works at the car dealership, right, your car salesman, does he need to know how to program to do his job? No, but he can put together things like, let's say I get if you get a web inquiry from a customer and you have a phone call, maybe you send like an automated text 2 days later, like, hey, it's Mike at the dealership, just checking in to see, and you can automate that sort of stuff, right? And if you wanted to program that, if you could do it in a graphical manner that somebody who doesn't have programming training can do, that increases their productivity, but also means they don't have to be a code monkey, right? And that's useful, right? There are plenty of examples of this kind of thing in the art world, like digital art tools, where you'll connect little things together that will change like material properties in 3D graphics or something like that, where, again, you want to give somebody a tool that's going to be comfortable for them to use and not be just a wall of Python text or something like that, because not everybody is keen on looking at just a wall of text. Okay, though, as I think you guys will start to see as we get into this, the visual programming is kind of like training wheels. And imagine that I put training wheels on a bicycle, and I put you on the bicycle, and I said, ride to the corner store and get some bubble gum. Or, yeah, go to the sketchy gas station and get some bubble gum, right? What would happen with the training wheels? Do you think they would actually hinder you? Yeah, probably, right? But if you were 5 years old and just learning how to ride a bike, would they hinder you? No, they're there for a good reason, but eventually they need to come off, right? So that you can do bigger and better things. Kind of the same thing with visual programming. So it's a great place to start. Great, again, for novices, but not the long-term way of programming, okay? So for our purposes, the little blocks of things that'll be there, in addition to being able to move things around on the screen or whatever, which is what Scratch was originally designed for, will have the capability of controlling the little digital pins that are sticking out the side to turn things on and off. We could read from sensors. So in the same way that Dr. Brown earlier in class, was asking, well, what is your phone capable of sensing about its environment?
That's got a gyroscope.
Yeah, it's got a gyroscope, it's got a temperature sensor, it's got a humidity sensor, it's got a pressure sensor, it's got a magnetic compass that's able to really, that only works outside. But it's got all of these different sensors on it that enable it to know which way you're facing, which is kind of useful if you're driving or something, right? Navigating. It knows the pressure, which means it can partly kind of figure out the altitude. It's also connected to cell phone towers, right? And using that can triangulate your position. Nowadays, like some of the newer Apple phones also have like some satellite connectivity for like super emergency situations. So you guys have probably seen the ads of like the dude hiking and he's climbing the mountain in the middle of a snowstorm and he still knows where he is because the satellite, he's got a satellite connection, which is kind of freaky that you can have that on your wrist nowadays. But yeah, so in the same way, you know, we've got kits of various sensors that we can plug in that do all of those same things. You know, we've got this one that's a pressure, humidity, temperature sensor, or that one that's a gyroscope, or this one that's an LED. And so we can wire up all these things and use the program to read information from those sensors and also make decisions based on it and send information back out or turn things on and off, right? So we could make like a stupid little traffic light program. What would that look like? How does a traffic light work? Yeah, you turn on the red light. There's some amount of time that needs to happen. And then you turn on the green light. And then there's some amount of time that needs to happen. And then you turn on the yellow light. And you wait a little while. And then what happens then? Yeah, it just goes into a loop, right? Well, now we're programming. Okay, so we can add all of the, you know, do all of that sort of stuff. Okay. Later, we'll move into more graphical programming that will look more like what you think of programming when you see programming, which is just to say, you know, things with text in them. Okay. Again, you'll see, I think, as we get into it, why the training wheels are good at the beginning, but when they need to come off. Okay. Now, this being a computer, well, like any other computer, let's say you write a Word document. Well, what do you do with that when you're done? Save it. Okay, you got to save it someplace, but then what? You maybe need to print it, or you need to upload it to Canvas, or you need to do any of those sorts of things. Okay, so the computer has, let me get to a picture of it. Well, you might want to be able to copy files from one place to another, or you know, put things onto like a USB stick or something. Well, how do you do that? Well, how do you do it on your computers you guys use now? You stick the USB stick in the side, and then what? Yeah, the little file manager comes up, you select what you want to copy, you find the destination where you want to copy it to, and what do you do before you pull the USB stick out? You do a little eject thing, right? All of that is exactly the same idea, it just may look slightly different, okay, than the way it does on Windows or the way it does on Mac OS. The file browser basically looks like this. You've got icons, you can switch to which view, so like do you want icons or do you want a list view? Same thing in any other operating system. And then over on the left, you see your directory structure. Now this is what's going to be a little different for those of you who are coming from Windows, but will actually be more similar for those of you who use a Mac. Okay? So on Windows, where is everything? Well, it's on a drive, but what's that drive called? C. Okay, the C drive. Yeah? And what folders exist within that drive? Yeah, okay. Desktop downloads, all of those things, those are actually subfolders of your user's directory, okay? So on the C drive, you would see a subdirectory called users. Within that would be the name of your user and any other users that use the machine. And then within that, you're going to have your downloads and your desktop and all of those sorts of things, okay? But everything's organized in sort of a file structure. And the paradigm for this is like manila folders that are stacked inside each other, right? File folders, right? And the icons even look like that. Okay, so we're all cool with that, right? So what things are called differs. On Mac it looks a little different, but the idea is the same. There's a place where your programs are, there's a place where all your user stuff is, there's a place where all the like core Windows or Mac components are that you're not supposed to touch, right? Same idea. Okay, so on y'all's, everything is going to be in a subdirectory, so instead of it being C, the main directory is just called slash. Okay, so the root directory. Within that is a folder called home, and within that are going to be subfolders for each user of the machine. Now, the way we've got these laptops set up, there is only one user. You each get your own, right? And the users are all called Pi. Okay, real creative, I realize. Your user has a password. Right now, they're all set to the default, which is 1, the number 1. Okay, so yeah. But what's within the Pi home directory? Well, a lot of things that are going to look really familiar, right? Like desktop and downloads and documents and so on. And where do you want to put documents or things that you're working on? Well, it's up to you to organize it, right? Where should you put stuff? How many of you guys put everything on the desktop? Okay, get out. No, you're, huh?
It's all organized in nice little folders.
Okay, but still, right? How you choose to organize your files is up to you, but don't be a complete moron when you do it, right? Use subfolders. So for example, on your main computers, you probably have subfolders for each of your classes, right? And maybe you do it by semester or something like that. Is Siri not able to find a connection? No. Oh. Well, tell Siri I also am having trouble finding a connection, but
It's tough in this time slot. These guys are pretty tired.
yeah. That's the first.
They didn't use break to refresh. Just wait till week 8.
Yeah. Yeah. That's why we have coffee. Do stupid things faster and with more energy. Okay. Okay. So, yeah, so organize your stuff the way you want. In terms of using the web, the program is called Chromium. So let me go back up to the main screen. Under Internet, or the little thing that looks like a globe, it's basically Chrome. It can do almost everything that Chrome can do, but it's not Chrome. It's sort of a slight variant of it. But signing it into Canvas, signing it into your email, like the Outlook Online thing, all of that works pretty much the way you would expect. It's just a little slower for web pages that have lots of stuff going on, like the email, for example. For printing, and this is the one kind of annoying thing, you're going to have to do the whole email it to yourself. Or what else could you do? Yeah, download it on a USB stick, or use the Box web interface and use Box that way. Any of those would work, but yeah, there's no way to print directly from these because of the way that the campus print system is set up. Okay, if you were doing this at home with this regular home printer, that's a different matter. But you know, with the whole like PC client paper cut nonsense, it's just no, it won't work. Okay. Did you have another question though? That was it. Okay. Yeah. So really though, for the most part, it's pretty much like any computer you've ever used before. Okay. With them, they all each kit has an external wireless mouse. The wireless mouse uses a single AA battery for power. And if you ever need a replacement AA battery, just swing by the place where you're going to pick up the laptops and ask for a battery, or just grab a battery. I'll maybe put a stack of them over in the library too, just for convenience. But I mean, they're mice. There is a little switch on the bottom of it to turn it off, and that would be a good thing to do when you're not using it, so that you're not draining the battery. Same thing with the computer. Okay, so it's not really rocket science using these things.
They also have batteries at Walmart.
Huh?
They also have batteries at Walmart.
They do, and at the sketchy gas station, right?
When you're picking up your urine.
Yes, exactly. Okay. So as we get into it, you guys will start to get a little bit more comfortable with using Linux. For right now, we'll do it basically only in graphical view, and everything will be nice and friendly. And then we'll start to teach you how to use the console and a few things like that. Under preferences, there's some configuration things. So for example, how many of you guys like the scroll wheel to be backwards from what it defaults to? Yeah, so like which way you want the scrolling to work or how sensitive you want the mouse, those sorts of things are all configurable. I mean, heck, you can set up alternate keyboard layouts if you want to be able to type in another language. They're defaulted to English, but, well, American English anyway. I put a few games on there just because it'll be kind of fun, because why not? And then we'll also be programming the things. Yeah, now my intent was that this would fire right up, but because of the screen, they have to do kind of a funny thing to get the configuration's a little funny, so I'll figure that out and have that fixed. All right, any kind of quick questions on the computery end of things? No, it's not rocket science. But they are computers, and they weren't cheap. Right? I mean, the whole pile of everything cost about 10 grand. So what happens if you lose something?
We owe you.
You owe me, right? What happens if you break something? Yeah, okay. So you'll sign these things out, and then at the end of the semester, you'll turn them back in, and if things are missing or things are broken, then I will fine you. And if you're a senior who's trying to graduate, guess what happens? Yeah, pay up or don't graduate. Right? So, yeah, anyway.
I point out that most of the equipment was through the generosity of alum, but in future years, you should be generous.
Yeah, a good pile of this, not every bit of it, but a good pile of this is, and a good pile of the equipment I'm using up on the table here is the Uncle Rob Special. How many of you guys know Rob Shook? Right? He's very generous to the college and been very generous to me. He's not the only one, right, that people donate to college, and that allows us to get cool toys and do interesting things. So in 20 years, when you've all made your millions and millions, I hope you'll remember the nice CS and physics professors.
Measuring their portfolio in gigadollars, right?
Yes, gigadollars. There you go. That's a term. Okay, so let's we'll sort of transition over to the lab part of the day, and so buddy up with somebody, and we're going to bust out the boxes. Okay. All right. So at this point, I'm going to kill the stream because there's no point in streaming the rest of this, and we'll pick up with the activity, and then I'll of course see you guys again on Thursday.